Hello everyone, welcome to my talk rendering in the browser. It's the first time I'm presenting in front of an audience, so don't be shy to stop me, ask me question, and or correct me if the code is bad. So my name is Antoine, and I'm gonna talk about to render in the browser or not to render in the browser. It's a question I have been asking myself a lot lately, especially working on offline rendering and stuff. The browser can do some incredible things, especially with Chrome being so it's heavy on memory and it eats a lot of RAM, but it can do some crazy stuff. I've included a picture of the Utah teapot because we're going to go through the history of rendering a bit later, and it's kind of the most representative image of rendering. So normally people present who they are at the beginning of the talk. My name is Antoine, as I mentioned. I'm 24 years old. I graduated from ATM in Cégep de Jonquière, which is a little college up north, the province. It's very good. I arrived in Montreal in 2015. I went to ISI and studied computer science. And now I'm a student in mathematics, making my major at UQAM. And I also blog a lot on CGI and multimedia's programming in general. And I work in the 3D/CAD industry. So I wanted to also mention a bit of my mentors for this talk. Starting from the left, Charles-Antoine Rondeau, which is an incredible source of discussion and inspiration, really there to always support me with those kind of geeky question. Even if he's not a geek, it's always good to make it somehow better to understand. And then François Pinchot, Patrick Bergeron, and Inuk Babin-Ruel, which are the three main engineers I worked in the last 2 years. They especially François Pinchot and Patrick Bergeron are very old original gangster soft image squad. They build a lot of the Montreal computer graphics community and so on. Alright, so line by line, we're gonna go through a little history of rendering, how I started writing my own rendering for the web, a bit of physics and mathematics of rendering. I don't want to go too deep, so if you're if you have some basic mathematics, you will not be losing the key of what it is, and also what it's next to come when it comes to rendering in a browser. So a brief history of rendering. I wanted to make a bit of history because rendering in a browser is something very new. And it started back in 1976 in the University of Utah, when some of the very old cats of the general computer graphic industry proposed a paper that allowed the computer to render Utah teapot. That's why it's called a Utah teapot. And it basically mapped around points around geometry. A bit later, there's been a lot of action in the field of geometry in action, especially how you can make meshes and stuff moving on the screen, and how you can change ray origin and highs and stuff, and change perspective of the camera. There's been some major algorithms over this subject. Really, there's going to be a frame next that goes through all the list of them. You could feel free to read them if you like to dive a bit deeper. But around 2001, there's been three guys so before diving to PBR, let's take a look on the Utah teapot. This guy's called Martin Newell, is English PhD, who went to the University of Utah and designed this kind of geometry, equation-based geometry. And he wrote this incredible paper that is called Displays on Display, and it goes over the origin of the teapot, so worth reading. The University of Utah is where David C. Evans, which is like the I don't want to say the godfather, but definitely one of the pioneer of modern computer graphics. So that's why everything is related to Utah at some point when you dive into the history of CGI. So list of all the rendering innovations. If you want to take a look on how we went through the basic raycasting to PBR, well, this is the way to go. Like the Wikipedia list all the years and the algorithms. And then comes PBR around 2004, when Matt Farr, who is now working at NVIDIA as a researcher, Greg Onfray and Pat Aranan proposed a book called Physically Based Rendering. I like to say it's kind of the new Bible, because it basically took all the things we had from this list and migrated it to a real-time rendering approach, which is really important when it comes to rendering in the browser, which is real-time rendering. Okay, and I want to talk quickly about what is physically based rendering. This talk is not it's not a physically based rendering talk, but it's basically a way, like if we get back to this frame, what Matt Farr and Wendy Jacom and Greg Onfray proposed was basically a way to make the computer render shapes and lights as they would behave in the real world. So instead of trying to mimic and try to find some and reinvent the wheels on how lights would behave, they would say, you know what, we already have like the Newton and the Maxwell equations of light, so why not just use them to create some more realistic rendering? And it turns out pretty well, as their book Physically Based Rendering is still one of the resources in modern computer graphics. So one of the main challenge when it comes to web is that we are not dealing with the hardware itself, such as normally, if you write some rendering or some code to render, you will have like the brain-hole OpenGL pipeline, and you could define your vertex and write some C++ code to register some buffers using the CPU and stuff. And you're really like close to the hardware. When it comes to web, you use some tools and APIs that allows you to write some code to interact with the browser, and then you just assume that the browser would make the task you want. So you cannot go near to the metal in web as you would do in general like software. I want to say software, but like OpenGL, Vulkan, or DX pipelines. That brings the WebGL pipelines in. It's very interesting because a lot of the modern architecture of browser relies a lot on memories. And the way, like if you are from a OpenGL background, diving to WebGL won't be a huge step. So, you have the kind of geometries and attributes. You could have like your vertex shader. You could like assembly them in a primitive way, rasterize them. Then you could apply a fragment shader, frame buffer, and have it on the screen. So I won't go through every step of this, but it's simply worth mentioning that the WebGL pipeline is not that much. Like if you are an OpenGL dev and you want to dive into WebGL development, like the pipeline of WebGL is not that much harder to grasp, just that you're dealing with JavaScript code and you're dealing with the API of the Chrome or any browser you're using, really. So I started to write graphic in the browser using Canvas and P5 or processing. I'm coming from a processing background, which is defined mostly by, let's say you have an image and you have a X and Y coordinate, and you could start to point vertices on the screen and stuff. When it comes to WebGL, it's kind of a different approach, such as you would have into a general like OpenGL approach of software dev. So a big part of graphic pipelines are shaders, and shaders are cool. If you want to explore more shader, go to read the book of shaders. It's a must read. But the shader in the browser does not work in the same way as you would expect them to work if you were shooting them like in here in your like the pipeline change from a GPU approach or hardware approach to a web approach. But therefore, you can take a look to the vertex shader code and see that you still have the same kind of flavor, which is like in C++ or in any other language that you would send a shader to your programming or your GPU. You would define a string or basically a file buffer. In JavaScript, you would define it the same way, which is like you would have like all the attributes and all the constant of OpenGL, but inside a browser this time. And then you would create a shader, and you can also have the fragment shader, and you know, like you record the shader, you compile it and stuff, and you can handle errors and stuff. So the pipeline changed a bit, but the code itself, if you're from an OpenGL background, won't be that different. As I mentioned, I come from a very JavaScript-ish, not JavaScript-ish, but much more like a canvas approach of coding graphics in the web. And one way I could basically define my shapes was just to create it's not the proper way to define a class in JavaScript, but anyways, you get the idea. So like you have a vertex which has a X, Y, and Z in 3D, or just for now 2D, which is a coordinate on a Cartesian space, and you can define the shapes using like vertices, which is like what we could define as vertex buffer in OpenGL. But it's all a matter of perspective, because when it comes to graphics, you deal normally with Cartesian coordinates, which is a Y, and you could like mess around. But when it comes to circular motion, sometimes you'd go back to spherical or polar coordinate, where you would have like a much more like theta angles and much more matty ways to describe the points around what you want to draw on the screen. So WebGL does it really better on this, especially when it comes to programming shaders. If you want to mess around with like the much more like theoretical approach of computer graphics, you definitely are better with WebGL than you are with Canvas. Especially, but like you could rewrite your own function switching to any of those polar coordinate to Cartesian or Cartesian to spherical and so on. So here's an example of shader. I'm not sure I'm gonna go to the code because I don't think it's so important, but you can see that basically you create shader, you register, you compile, you could check for error, then you return the shader, kind of basic stuff. And the browser does really well at real-time rendering, especially with the 3GS. You could go on their website and check everything they've done. It's crazy to see how the architecture of modern hardware is well designed to deal with the browser implementation software sides. Okay, so now we're gonna take a look to how to cast. Because most of the time when it comes to rendering, most of offline renderings works with ray tracing algorithms, which is basically just a super like cheap image here, but you have your perspective and you shoot the rays through every pixel, and then it collides the shapes, and then you could define the color of what you want to render on a 2D perspective, therefore an image. A lot of graphic programmer tends to deal with sphere casting because it's kind of the way to go. So let's say you have a sphere starting at pointer C, and you have a ray, which is basically a vector with the origin, and you have a V, which change then to infinity. You can cast where the rays intersect with the object geometrically. So you could make like the matrix dot product. So let's assume you have a normal pointing 90 degrees up from a surface, then you could cast it to obtain a 0, and then say, okay, so like my rays actually intercept the sphere. So there's two main ideas behind rendering that's being offline, real-time, or in a browser, which is the geometrical approach, which is like you define some shapes, and there's the algebraical approach. As you can see here, the O plus TD to square minus R square is because I tend to prefer using the algebraical way to define some step, because we can therefore use a function just to find so this is basically like a quadratic function that we can therefore process to get the zero of an object. So like if you have a ray origin, which is here, and you can say that it has two intersections, one intersection, at a center, no intersection, and so on and so on. So that's like the geometrical way to do it. So you would deal with bunch of like trig functions and stuff and vectors processing, but when it comes to analytical, you have a much more elegant ways to define it. So sphere in the real world, it's kind of boring to just render this sphere. In the real world, you'll have some shading and stuff. So I want to dive a bit in shading, because I think it's an important part of what WebGL can do and what you can achieve in a browser in such an easy step. Normally in your computer graphic books, you would have like a triple integral being the points x and y and z, and you would integrate it to find the error rate, which is somehow could be handled as the shadow. But when it comes to computers, like, you don't really want to use integral. You prefer to use sum and use it in a discrete way. So you need to discretize the signal. So that's basically how you would do it. It's not the perfect equation of like how you would handle a perfect shadow, but still you get the idea. So instead of like dealing with triple integrals, you would simply sum the change and then have the error rate being pointed, and you can handle the sphere in a real world place. So browser is very good when it comes to rendering. There's incredible stuff happening. There's this thing called light tracer, which is basically the I think is the most cutting edge research product that happened in the WebGL and browser rendering graphics industry lately. You can go check their website. It's incredible how much they achieve to grind the GPU and have a decent feedback in the browser. So browser is good for rendering and stuff. So well, I guess it's just a way to start exploring a bit more. If you're coming much more from a software side, definitely it's worth checking a lot to the browser side of rendering. And therefore, it's the end of the presentation. So thanks for listening. And if you have some questions and stuff, it would be a nice pleasure to talk a bit about the general ideas that were proposed in this talk. And thank you.